Section 404.7b of the National Electrical Code, or NEC, mandates X2 grounding for Class 2 and Class 3 remote control, signaling, or power-limited circuits. The acceptable level of harmonic distortion hinges on the equipment and circuit in question. As a general rule, aim for a total harmonic distortion, or THD, of less than 5% for voltage and 10% for current. Triplen harmonics, which include the 3rd, 9th, 15th, and so on, can indeed pass through a single-phase transformer. However, their intensity will be notably reduced because the primary winding of a single-phase transformer lacks a neutral connection. If present in excessive quantities, triplen harmonics can wreak havoc on circuit boards. They induce ground currents within the neutral conductor, leading to a voltage increase in the neutral to ground, or N-G voltage. This elevated voltage can then inflict damage upon sensitive electronic components housed in the circuit boards. The initial assessment that harmonics from all three cabinets are converging on the neutral, causing it to overload and subsequently triggering the voltage rise on the N-G, is a sound one. This scenario is common when multiple nonlinear loads, such as transformers, share a common neutral conductor. To combat this issue, consider these recommendations. Firstly, install harmonic filters to curtail the amount of harmonic circulating within the neutral conductor. Secondly, if feasible, isolate the neutral conductor for each individual cabinet to prevent the aggregation of harmonics. Thirdly, verify that the transformers are properly grounded to minimize the voltage rise on N-G. Fourthly, continuously monitor the N-G voltage to ensure it remains within safe limits. Fifthly, limit nonlinear loads. Reduce the number of nonlinear loads on the shared neutral conductor to minimize harmonic distortion. Now delving into the specifics of harmonics, it's crucial to understand their origin and impact on electrical systems. Harmonics are sinusoidal voltages or currents having frequencies that are whole number multiples of the fundamental frequency. In a standard power system operating at 60 Hz, harmonics would include frequencies like 120 Hz, 180 Hz, 300 Hz, and so on. These harmonic frequencies distort the pure 60 Hz sine wave, leading to various problems. Common sources of harmonics include nonlinear loads. These are devices where the current is not proportional to the voltage, such as electronic devices, variable frequency drives, switching mode power supplies, and, as observed in this case, transformers. Transformers, when subjected to non-sinusoidal currents, can themselves become harmonic sources. The core of the transformer can saturate, leading to the generation of harmonic currents. The triplen harmonics specifically warrant special attention. These are odd multiples of the 3rd harmonic, such as the 3rd, 9th, 15th, and so on. They are particularly troublesome in three-phase systems with a neutral conductor, as they are additive in the neutral. In a balanced linear three-phase system, the neutral current should ideally be zero. However, the presence of triplen harmonics causes these currents to add arithmetically in the neutral, leading to a potentially overloaded neutral conductor, even when the phase currents appear balanced. The grounding of the X2 terminal of the control transformer is crucial for safety and proper operation. Section 404.7b of the National Electrical Code, or NEC, mandates this grounding for Class 2 and Class 3 remote control, signaling, or power-limited circuits. Grounding the X2 terminal establishes a reference point for the secondary voltage, preventing voltage fluctuations and ensuring that the voltage remains within safe limits. Without proper grounding, the secondary voltage can flirt, leading to erratic operation and potential damage to connected equipment. The high levels of third-order harmonics observed in the transformer primary are a significant concern. These harmonics can cause increased heating in the transformer, leading to reduced efficiency and a shortened lifespan. They can also interfere with the operation of other equipment connected to the same power system. The random peaks in the N-G voltages exceeding 5 volts indicate a serious issue with the grounding system or the presence of excessive harmonic currents. Ideally, the N-G voltage should be close to zero. A high N-G voltage indicates that the neutral conductor is carrying excessive current, which can be caused by harmonic currents or an imbalance in the phase currents. This voltage rise can damage sensitive electronic components, as they are typically designed to operate with a very stable and clean power supply. To mitigate the harmonic issues, several strategies can be employed. Harmonic filters are devices designed to reduce the amplitude of specific harmonic frequencies. They can be installed at the source of the harmonics, such as at the output of the variable frequency drives, or at the point of common coupling where multiple loads are connected to the power system. Harmonic filters typically consist of tuned circuits that provide a low impedance path for the harmonic currents, diverting them away from the rest of the power system. Isolating the neutral conductors for each cabinet can prevent the harmonic currents from adding together. This involves running a separate neutral conductor from each cabinet back to the main service panel, ensuring that the neutral currents from each cabinet do not mix. This can be an effective way to reduce the overall harmonic current in the shared neutral conductor. Ensuring proper transformer grounding is essential. This involves verifying that the grounding conductors are properly sized and connected, and that the grounding system meets the requirements of the National Electrical Code, or NEC. A properly grounded transformer will provide a low impedance path for fault currents, helping to protect equipment and personnel. Monitoring the N-G voltage is crucial for identifying and addressing harmonic issues. This can be done using a multimeter or a power quality analyzer. The N-G voltage should be monitored regularly to ensure that it remains within safe limits. A sudden increase in the N-G voltage can indicate a developing problem with the grounding system or the presence of excessive harmonic currents. Reducing the number of nonlinear loads on the shared neutral conductor can minimize harmonic distortion. This can involve replacing nonlinear loads with linear loads, or distributing the nonlinear loads more evenly across the different phases of the power system. It is also important to ensure that the power system is properly designed and sized to handle the expected harmonic currents. Now let's dive deeper into the technical aspects of harmonic mitigation. The choice of harmonic filter depends on the specific harmonic frequencies that need to be addressed. Passive harmonic filters consist of tuned inductors and capacitors that provide a low impedance path for the harmonic currents. Active harmonic filters use electronic components to actively inject currents that cancel out the harmonic currents. Active filters are more expensive than passive filters, but they are also more effective at reducing harmonic distortion over a wide range of frequencies. The size and rating of the neutral conductor are also important considerations. The National Electrical Code, or NEC, provides guidelines for sizing the neutral conductor based on the expected harmonic currents. In general, the neutral conductor should be sized to carry at least the maximum unbalanced load, plus any additional current due to harmonic currents. In some cases, it may be necessary to upsize the neutral conductor to handle the harmonic currents. The grounding system should also be designed to handle the harmonic currents. The grounding conductors should be properly sized and connected, and the grounding electrode system should provide a low impedance path to ground. A high impedance grounding system can exacerbate harmonic problems, leading to increased voltage distortion and equipment damage. In addition to the measures mentioned above, it is also important to consider the overall power quality of the electrical system. Power quality refers to the characteristics of the voltage and current waveforms, including voltage sags, voltage swells, transients, and harmonic distortion. Poor power quality can lead to a variety of problems, including equipment malfunction, data loss, and increased energy consumption. A power quality analyzer can be used to measure the power quality of the electrical system and identify any potential problems. Power quality problems can be addressed through a variety of measures, including installing surge suppressors, voltage regulators, and uninterruptible power supplies, or UPS. These devices can help to protect equipment from voltage sags, voltage swells, and transients, and ensure a stable and clean power supply. It is also important to regularly inspect and maintain the electrical system to identify and address any potential problems before they can cause damage. This includes checking for loose connections, corroded conductors, and damaged equipment. A well-maintained electrical system is essential for ensuring reliable and efficient operation. In the specific case of the HVAC control cabinets, it is important to consider the impact of the variable frequency drives, or VFDs, that are often used to control the speed of the motors. Variable frequency drives are a major source of harmonic currents, and they can significantly contribute to harmonic distortion in the electrical system. To mitigate the harmonic currents produced by variable frequency drives, it is recommended to install harmonic filters at the output of the drives. These filters will reduce the amplitude of the harmonic currents, preventing them from propagating throughout the electrical system. It is also important to ensure that the variable frequency drives are properly grounded, as a poor grounding system can exacerbate harmonic problems. In addition to installing harmonic filters, it is also possible to reduce the harmonic currents produced by variable frequency drives by using drives with built-in harmonic mitigation features. These drives use advanced control algorithms to reduce the harmonic currents, and they can be a cost-effective alternative to installing external harmonic filters. It is also important to consider the impact of the control transformers on the harmonic distortion. Control transformers are often used to provide power to control circuits, and they can be a source of harmonic currents if they are not properly designed and sized. To minimize the harmonic currents produced by control transformers, it is recommended to use transformers with a low impedance and a high level of isolation. It is also important to ensure that the control transformers are properly grounded, as a poor grounding system can exacerbate harmonic problems. In summary, troubleshooting harmonic problems in HVAC control cabinets requires a systematic approach that includes identifying the sources of the harmonics, measuring the harmonic distortion, and implementing appropriate mitigation measures. The key to successful harmonic mitigation is to address the problem at its source and to ensure that the electrical system is properly designed, installed, and maintained. Remember to always consult with a qualified electrician or an engineer when troubleshooting and addressing harmonic problems, as improper installation or mitigation can lead to further damage or safety hazards. Considering the location in Indiana, it is important to be aware of any local regulations or requirements regarding harmonic distortion. Some jurisdictions may have specific limits on the amount of harmonic distortion that is allowed in electrical systems. It is also important to be aware of any utility company requirements regarding harmonic distortion, as some utilities may impose penalties for excessive harmonic distortion. By following these recommendations, it is possible to effectively troubleshoot and mitigate harmonic problems in HVAC control cabinets, ensuring reliable and efficient operation of the equipment and protecting the electrical system from damage. Moreover, regular maintenance and monitoring of the electrical system can prevent future harmonic-related issues. Understanding the principles of harmonics and their impact on electrical systems is crucial for any electrical professional. This knowledge allows for proactive measures to be taken, minimizing the risk of equipment failure and ensuring a safe and reliable electrical environment. This detailed explanation should provide a comprehensive understanding of the topic and guide you in effectively addressing harmonic issues in HVAC control cabinets.